Just to let you know.
All right. So, welcome everybody. My name is Bruce Griffiths. I'm an assistant professor of biology here at Kentucky State University. My training is in neuromuscular physiology. So, back in graduate school, I studied muscles and nerves and how they talk to each other and what effects those had on each other. And so I worked some in what we call in vitro, meaning you grew the cells in a dish. And I worked some with animal preparation. So I worked with mouse culture cells and I worked with crayfish muscles. And so what we're going to do today is an introduction to electrophysiology. Now, one of the things that I should have mentioned to Jeremy before but forgot today was that before we start any uh, experiments with any kind of animal model, we always want to get review and approval by what's called an institutional review board. So today we're using this as a demonstration activity, and these are great for those activities. But if I were going to start recording data and then trying to compare data sets from different individuals, I would have to have lots of permissions to do that in order to protect those individuals' personal privacy. So what we're doing today is all purely demonstration, and we're going to start out with an unboxing. But before we do the unboxing, it's very important that we know what we're using and where we got it. So what I have here is a Muscle Spiker Box Pro kit from Backyard Brains, and we'll look at that website in just a moment. And additionally, we have a reflex hammer. So we're going to work and see how well we can get these to work today. The reflex hammer may be an extension that we don't get all the way to. So hopefully you've already unboxed these. If you haven't, we're going to unbox it together. Before we can do any of the recording to make things really cool, we need to download some software. So let's see. I'm going to try to share my screen here. Well, of course, that didn't work so well because I limited my screen. There we go. I figured out how to do it again. Sorry that I'm having to look away from camera, but it's hard to keep the camera and everything on focus. So you should be seeing the Backyard Brains website. So this is the main entry page. What we can do to get there quickly is just go to experiments, and then you want to look for the recording electricity from your muscles, or you could even do the antagonistic muscles from the Spiker Box Pro. So you could go back, and the one right next to it is the agonist and antagonist pairs. You can click on that. It's going to have explanations of what we're doing. So I'm scrolling through this very quickly on purpose because I don't want you trying to read that right now. But then what you also will want to do is if you go to the store, you can scroll down, and on the left-hand side at the store, you'll see software. So it's important that you download the software. The cool thing about this software is it's free, but you can download it for your phone, whether it's Android or a Mac, Apple, iPhone. You can download it, and then once you get it downloaded, you can even, if you're super technically minded, you can have it set up for Linux or Arduino. You can put it on the computer. I'm going to be using the computer today so that we can do 2-channel recording. So if you hear something called 1-channel or 2-channel recordings, 1-channel means you can get information from one source and record it. 2-channel means you can record from 2 sources. And so that's going to be important for us in a little bit. So if you haven't gotten that software already, I encourage you to go ahead and get it now. All right, so let's get into our box. So first of all, before we get anywhere else, thank you, Jeremy, for posting that website. Let me just see if you all can use your reactions or not. So if you look at your reaction button down at the bottom on Zoom, let's everybody see if we can give me a thumbs up, because that's going to be a quick and easy way for me to see if people are understanding what's going on. If you can just give me a thumbs up, if you're not on video, just a thumbs up reaction helps me know what's going on.
Yeah, and let me just say, if anybody has trouble or just wants to stop, please use the chat or some other way to let us know. Don't let us keep going and you're hung
Absolutely. Don't feel bad about interrupting me. This is a learning experience. So if you have a question, even if you don't have the kit in front of you and you have a question, please ask it, because your questions can lead to discussion, and discussions lead to more questions and more thinking is always a good thing. So I'm going to show us the kit, and I'm going to move the camera a little bit here. So pardon the vertigo if you get any. So this is a really cool kit. And this is the old version. So here's the old version, and we've got the new version, the Pro version. And it's a lot better because of the 2 channels. All right, first thing they have on the top is the information about what's included, and there's information about how to set it up. We're going to go through this setup, and then there's even information about getting the software, and then 4 sets of experiments. We're really going to focus on this first one and maybe the second one today. So we've got some recording electrodes. So these are patch electrodes. They're sticky. They just stick onto your skin. And so they're going to be able to record electrical activity generated by our muscles. We have a little package of essentially popsicle sticks with some electrode ends on them. And electrodes really can be anything metal. And as long as they conduct electricity, and you'll see that these are really fancy electrodes. You've probably seen these kinds of little pins and clips around places before, but these are metal and they're conductive, so they will conduct the electricity, and we could use them for recording from very small muscles like the muscles in your hand versus the muscles in your arms or legs. Of course, we have a lot of wires, and we have the main kit piece, which is this. This is the Spiker Box Pro. There will be an unattached 9-volt battery that you have to remove some plastic off of and then get inserted. There's only one way to correctly insert it. It takes a little bit of effort, but once you get it inserted, it's ready to go. If you're going to store this for a long period of time, I would recommend taking the battery out so that you don't just have the battery in there all the time. The orange wires are our recording electrodes. And so we're going to talk about how to hook up the cable and the recording electrodes in just a moment. The information will say blue cable, but this is a black cable. This is a USB to USB-C cable. And so we're going to, or mini USB to USB cable, and we're going to use this to connect to the computer. If you don't have a computer, but you downloaded the app on your smartphone, then you can use the smartphone cable. On the smartphone cable, you'll notice one side that says Spiker Box and the other side that says smartphone. This just goes into your microphone jack in your smartphone. You will notice that the ends are different. So the ends aren't identical. So it does matter that the smartphone goes into the smartphone and the other end goes into the Spiker Box. Again, I'm going to be using the USB cable because I have the computer set up. There is some conductive gel in here in case you were going to, you might have to put a little of this on to help get the signal more clearly. You could also just scrub the skin off very easily. Scrub the skin, just some soap and water, that will work, just to get some of the oils off that might interfere with the signal. So this is all very color coded, so it's pretty intuitive to put together. So we have two of these orange, and if you look, there's a little cockroach design on there because that's the symbol for backyard brains, is a cockroach. Because cockroaches are used in a lot of neuroscience experiments, because you can, at certain periods of the cockroach's life, you can remove a leg and it does not harm the cockroach. And if it's at an early enough stage in its life, it will actually grow the leg back. So there are lots of reasons to use cockroaches. They're easily obtainable. They're invertebrates, so there's less that you have to do in terms of approvals. But I'm just going to get everything set up here before we get going. So I'm just going to go ahead and connect this last cable. So instead of just coming in and having it all set up, I thought I would show you to set it up. The flat side on this little mini cable goes up, and make sure you get it inserted all the way, and it kind of just stops. So don't keep forcing it, it will stop. Now we'll hook that into the computer. So I've got all that hooked up. But what about the muscles, right? So I've got to hook me up. So let's start off. Let's talk about this idea of muscles. So does everybody know your muscles generate electricity? Did you all know that? Hopefully you knew. Our muscles generate electricity. So without getting into too many details, if we were to look at a super magnified view of a cell membrane, it would be very, very thin like this, and there'd be two sides. And on each side of the membrane, we would have some positive charges and some negative charges lined up and kind of attracting to each other. So we all know what I call our kindergarten chemistry, opposites attract. So those attractions are there. And so there's an unequal balance in these two compartments. So in physiology, we like to talk about compartments. We have the extracellular compartment and the intracellular compartment. So the charges aren't equal on either side of the membrane, and so that creates a difference, and that difference is what we call a membrane potential. So when we decide to contract our muscle, we send the signal for our brain usually, unless it's a reflex. It goes down to the spinal cord. From the spinal cord, motor neurons send the signal out to our muscle, and then that signal on our muscles gets turned into an electrical signal, and then that results in contraction like this. So, all right. So let me slow down for you. All right, thank you. I get talking fast because I get excited about this stuff. So, very good. So, if we're going to talk about the electrical signals in the body, we're going to talk about how on a cell, there's a cell membrane that's really, really thin. And just for an example, we could think of it as this piece of paper. And on one side of the piece of paper are going to be some positive charges, and on the other side of the piece of paper are going to be some negative charges. And they're going to be talking to each other, if you will. They're going to be attracted to each other through that paper. So think about at home, you might have magnets holding up a picture or a good test score up on the refrigerator. That magnet can interact with the refrigerator metal, even though there's a piece of paper in between, so that piece of paper separating. The same thing happens with our cell membranes. The cell membrane separates those charges outside of the cell from the inside of the cell. And the difference in those charges, and it's teeny tiny differences in our cells, are going to create what we call a membrane potential. And it's really a membrane potential difference. So let me see if I can get somebody to tell me a definition of a basic biology definition of energy. Anybody know the definition for energy from a biology perspective? I know we've got chemistry and physics experts out there that probably give you a much better definition, but a basic biology definition for energy.
Feel free to use the chat or to unmute yourself and just blurt it out. We won't ridicule you if you're wrong, I promise.
Anybody have a definition? We say it all the time. I don't have much energy today. Walk, don't run. You've got too much energy.
Someone in a private chat offered work, able to do work.
Perfect. It's the ability to do work. That's a great basic definition for biology right there. So energy is the ability to do work, and we often talk about grouping that into two main types of energy. One type we call kinetic energy, which is the energy of motion. So I'm a little kinetic right now. And then we talk about potential energy, and that's stored energy. So usually we can talk about stored energy being things like you have a book on the top of a bookshelf. Something happens, that book falls, it makes a very loud noise as it hits the floor because that energy has been transferred. So we talk about energy transformations and energy transfers a lot. But for us, when we're talking about the cell membrane, it is helping to store some potential energy. So when we send these signals from our brain down to the spinal cord, from the spinal cord out to the muscles to cause them to generate this electrical signal, we're releasing some of that stored energy, and it's being carried across that cell membrane to change the voltage or to change the membrane potential. We're not going to get into all of the mathematical calculations, although there's some really cool math involved. And so you can actually talk about chemistry is going to help you understand the biology. And of course, the physics is going to help you understand the chemistry, and the mathematics, as we saw this morning in the video, is going to tie it all together, which is really important. So let's talk about some anatomy for a moment. If I'm going too fast, just let me know. But just keep in mind, we're going to do work. So in terms of the body, if I take my arm and I bend it this way, I've done work. I've moved my body. If I extend my arm that way, I've moved my body. So we're going to focus on this joint, the elbow. So if I move the arm this way, I made the angle of the elbow smaller. We call that flexion. So the definition of making the angle smaller is flexion. If you make that angle larger, we call that extension. So as somebody that teaches human anatomy, sometimes we'll talk about flexing our muscles. Your muscles don't flex. It's your joints that flex. Your muscles contract. I know, terminology. So let's talk about agonists and antagonists. So those are some special terms we use. So muscles that work together, like the muscles that allow your arm to flex at the elbow, those muscles that work together we call agonists. So agonists work together. Antagonists do the opposite. So without even knowing anything about the names of these muscles, you know that these muscles are going to contract and they're going to make this angle smaller or flex the elbow. And if I contract these muscles on the other side, they're going to extend my arm at the elbow. So flexion at the elbow, extension at the elbow. Flexion at the elbow, extension at the elbow. The muscles we're going to work with today are called the biceps brachii muscle. Your biceps muscle is what we usually hear about people talk about. Work your biceps out, do some lifting of weights. So we're going to work with our biceps and we're going to work with our triceps. So these are antagonistic muscles. So the first thing we want to do is make sure we can measure a signal from one of these sets of muscles. So what I've done is I've put two of these sticky electrodes on the outside of my skin at the biceps muscle, and I've got one on the back of my hand. Now, I've got two alligator clips that are color coded red. Red is for recording. The black color coding is for the ground electrode or the reference electrode. So whenever we're doing electrical recordings, we have to have something to refer to on the outside of what we're trying to record or away from what we're trying to record so we can gauge the difference in the signal. We're doing what's called extracellular recording. So we're not inside the cell. You can do that. You can take measurements from inside of a cell, but you would need a lot more equipment than what we're going to use today. So I've got my electrode patches in place. They have these little metal studs on them, and I'm just going to put my alligator clip on. And I'm going to put the alligator clip on the back of my hand. So now I'm ready to go. So I'm not even going to show you what I can do with that Spike Recorder app. All I have to do right now is turn on the machine. So I'm going to turn on. So how do I turn it on? I just click it. So if I click it, turn it on, you might hear a little hum. That's just what we call background noise. It's probably reverberating a little bit through the system. But let's see if we can hear anything if I flex my arm at the elbow. I've got it hooked into the computer. That's why it's not playing out loud. What if I unplug this for a moment? Let's try that. When in doubt, switch channels.
Hey, Bruce, there's also a setting, since you're sharing your screen, in the bottom right, there's 3 dots. And if you click that, there's an option in there to share your computer sound.
Well, this sound isn't from the computer.
Oh, okay.
Or shouldn't be. So let me just disconnect some things there. There it goes. So this has a speaker on the bottom. So I'll turn it this way. And y'all can tell me if you hear this.
We definitely hear it.
All right. So that sound that we're hearing, that kind of, some people say it sounds like raindrops or something like that. So I'll just come out here so you can see what I'm doing. So that sound is a representation of the electrical activity on the muscles. So we're going to look at what that looks like visually in a minute, but that's a cool thing to be able to hear. So if you can do that, you don't even have to have the computer hooked up, smartphone hooked up, or anything. You can tell it's there. Now, here's something. I want you to watch this. So watch my arm and listen carefully. So watch my arm and listen carefully. So here we go. One more try. Now I'm going to flex my elbow again, but I'm going to turn my wrist over. What just happened?
Chat or unmute yourself and blurt out an answer. We have a mystery here.
What just happened? I was able to flex my elbow without making a sound on the device. How do you think that happened? This is especially for all of you student participants. So if you hear about it in class, when people say, oh, in the scientific inquiry process, you make an observation. We just made an observation. Something was different. So Let's do it again in slow motion. All right, I'll scoot back a little bit. Here we go. You ready? Okay, there's one. There's two. One, two. So here's something you can try where you are right now. You don't even have to be hooked up to the machine. I want you to take and I want you to feel your muscles of your upper arm. And I want you to do the same thing. Flex your arm this way. Let it down, flex it up, let it down. Flex, extend, flex, extend. Now I want you to turn that over and do it again. Did anybody feel a difference? Ray, you weren't sure before. Do you feel a difference?
Can you hear me? Oh no.
I realize I'm not a bodybuilder, but maybe if I get a little closer, we could even see on my muscle. We might even be able to see a difference. So I have my hand like this. So I'm going to watch right here. Now I'm going to turn my hand over. What do y'all think? Any ideas?
Yeah, we have somebody offered in the chat muscle tension being somewhere else.
That's exactly right. That's exactly right. So the muscle tension, when we have our hand this way, is primarily coming from the biceps brachii muscle. But there's another muscle right here, right next to it, called the brachialis. If our hand is turned over, what we call a pronated position, or thumb to the inside, the biceps brachii muscle does not help us lift anything. So if you want to lift something heavy, have you ever tried to lift something heavy? Maybe a bucket of paint or a grocery bag or something, you try to lift it heavy, you don't lift it this way, do you? That brachialis muscle is a lot more puny than the biceps brachii muscle. Usually if we want to lift something heavy, we're going to turn our hand this way. Lift, lift. So yes, we've got the biceps brachii muscle. We can record from it. It's activating. So the biceps brachii and its partner, the brachialis, are muscle agonists to flex the arm at the elbow. So they work together to do that. So it's pretty cool. So we've got our electrodes on the big muscle. We've got our ground electrodes, so we can record that. Now I'm going to hook things up to the computer, and hopefully this will all go more smoothly because I did practice this earlier. I do have it practiced. I just have to hook everything up. The hardest part should be getting my recording electrodes hooked up to my triceps brachii.
So the muscle has to be activated with a pulse of energy. And then if our little machine is placed on that muscle, it's reading when the electrical charge is being applied to that muscle. And when it stops, it stops.
So yeah, so the way this works, it's a really interesting system, the way our body works. So the neurons, or our nerve cells, starting at the brain for a controlled movement like this, an intentional movement, are going to send an electrical signal to another cell down the line. And there's a little gap between those cells, and they actually release what we call neurotransmitter chemicals into that gap. And then that neurotransmitter chemical can start an electrical signal in the next cell. So the way it works, when that electrical signal gets to what we call the neuromuscular junction, the little connection point between the nerve and the muscle, it's going to release a neurotransmitter we call acetylcholine. You don't have to remember that, just save it for later. That chemical starts an electrical impulse on the muscle because that chemical binds to something that acts like a door in a room. And when that door opens, it allows ions, or these charges, to cross the membrane, and that's going to change the membrane potential. That spreads down the muscle. When that spreads down the muscle, it's going to allow calcium to be released into the muscle. I'm trying to not get into too many details here. That calcium binds to other things. Now, I'm a physiologist, and I like to sum up physiology in one statement. And this really goes for biology a lot too. If you change the shape, you change the function. So when calcium binds to certain proteins, it changes their shape in the muscle and allows our muscles to contract. So we need calcium to help contract our muscles. So that electrical signal that is generated on the muscle cells is what we're recording. And that is in response to the nervous system. Now, if you have a muscle cramp or something, you can have it generate kind of spontaneously sometimes. Let me see if I can get this. Oh, I've got to minimize for a moment so that I can get to the recording software. We do have, if you are on the Backyard Brains website, you can also find PDFs. They have links to PDFs of these experiments. They're really cool. So let me see here. Oh, I better turn on the system. There we go. So let me go back and share my screen now. Okay. And I do want to share any computer sounds, but I don't think we'll have any sounds. So this is the spike recorder, and right now it's hearing the microphone. I'm going to click on this, which is the USB, and notice all that microphone sound went away. So all the microphone sound went away. So you should see some little fluttering on there. That's what we would refer to as 60 cycle noise. That's just basically because there's lots of electrical cables hooked in right now in the battery and things like that. I don't know if I unplugged it, if that would change it or not. We're not going to worry about that. So let's try this again. Now I can see, notice that those things are coming up when we hear the sound, right? And just a while ago, we talked about turning our wrist over. So let me turn my wrist over and do this again. So I'm not recording anything from the biceps brachii because it's not working. It's not being activated. But if I turn my wrist back over, that's pretty cool, right? So let's see here. I'm going to go into settings. I want to turn on channel 2. Oh, channel 2 came out at the top. That's kind of interesting. All right, that's fine. Channel 2 remembers my triceps brachii. Now, I'm not going to record anything until I put that onto a ground electrode. So I'm going to hold this, sorry, so many wires on one arm. I'm going to hold this electrode in my hand. So I'm going to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120 I'm going to let my arm
Somebody
go.
asked in private chat if the height of the signal is translatable to how hard you're trying.
Yes, it is. So I'm going to slow down a little bit on purpose because I don't want to confuse anyone. So first of all, let me go back. I want to take a recording here. Okay, so I've got a recording. I can go back to that later and look at that recording. But your question is really good. So remember, I said that we have neurons that are talking to the muscles, and muscles aren't just one big cell. There's thousands upon thousands of cells in my biceps brachii muscle. So they look like straws packed together in a container, like you might see at a restaurant somewhere where they have straws and you've got this whole big bundle. Or think spaghetti in a box. That's how a muscle looks. Each one of those pieces of spaghetti would be a muscle cell or a muscle fiber. So when we talk about this idea of how hard we're trying to do something, we can talk about what's called motor units. So a motor unit has a really simple definition. I'm going to turn it down. It was a little bit loud there for me. Let me see if I can type in this definition here. Well, I'm having trouble getting back to the chat, Jeremy, so you might be able to type it in for me. But a motor unit is one motor neuron and all of the muscle cells it controls. So we have one motor neuron controlling some number of muscle cells. So in anatomy and physiology, we might talk about having different sizes of motor units. So some muscles have motor units that are 3 to 10 muscle fibers big. So if you only have 3 or 4 or 5 or 10 muscle fibers in that motor unit, that means that each motor unit cannot contribute a lot of strength to a contraction of a muscle, but we have this other thing that we call recruitment. So this is where you're getting to with your idea of how hard we're trying. So for example, I go back and I pick up these popsicle stick electrodes. Oh, wow. Popsicle stick electrodes. Let's see here. Let's see what this looks like with the popsicle stick electrodes. Not a lot going on there. What if, I got crazy and I said, I'm going to lift this table off the floor. I'll stand up so I can get a good grip on it. Oh, the table didn't move, but we can see a lot more muscle activity, right? So you're exactly right about how hard we're trying. This is this idea, again, of recruitment. So our bodies do this automatically. So they start with kind of a small number of motor units and say, okay, you all contract and you should be able to lift whatever that object is or perform that movement for us. If that doesn't work, we recruit more motor units and more motor units and more motor units in trying to overcome the resistance of whatever we're trying to move. So if I have something that's attached to the floor like this bench, I'm not going to be able to move it. But if I have something like those popsicle sticks electrodes or this description pamphlet, I don't have to have very many motor units activated to move my arm. So what you've then come up with is along the lines of a research question or an investigation about how would this look different if we used, say, different weights and had somebody lift different weights, how much weight would be necessary, for example, to get it to the maximum amount? So I can do this without a weight and just squeeze as hard as I can, but that doesn't tell me how much weight would be necessary for me to get to that point. So that's something that you could think about doing is, all right, what would this look like if I lifted uh, an envelope? What would it look like if I lifted a can of soup? What would it look like if I lifted my backpack?
Oh, we
What would
have
it
a
look?
perfect question with that. Miss Rogers asked, what if you're trying to do a job and you simply don't have enough motor neurons to recruit?
All right. So, yes, that's a great question. So, if, for example, uh, I tried to lift something and I've recruited, so all my motor units are activated. So, all the motor neurons that control the muscle fibers, they're all activating, and every single muscle fiber in the whole muscle is activated. And if that weight or that resistance is too much, I won't be able to move it. So if I'm trying to lift something very heavy and, maybe I'm at a job and they say, here, hold this, you might have somebody that has a lot stronger muscles than I do try to hand me something that weighs more than I can carry. What am I going to do when they give it to me? Am I going to be able to carry it? Nope. It's going to drop, right? So that's why if you ever see some of these boxes, they might say that have something very heavy in them. They will say something like team lift, meaning that you can't have one person try to lift it safely. You need more than one person. Uh, so that's a really good question. If you get to that point where you can't lift it, we're not getting there today, but you can actually have your body say, you know what, we're going to stop trying to lift this because it could be causing us damage. So we have actual sensors in our bodies that tell us about our muscle contractions. So that's another cool thing. So for example, at the risk of looking a little silly, I've never been afraid of looking a little silly. I do it most of the time. I'm the one on camera, so don't worry about this. But if you're not on camera, feel free to play along at home. So I'm going to stop sharing the recording screen right now. So feel free to play along at home. Can you find your nose? I found my nose. I can even find it with my left hand. I'm right-handed. Okay, watch this. I'm going to close my eyes and find my nose. What? Okay, that sounds pretty easy, right? So let's do this. What if I close my eyes and wave my arms around? Can I find my nose? How am I still able to find my nose? Our brains have a picture of our body. It doesn't look like our body. Our brains have a picture that's based on the amount of sensory information that comes in and the motor or movement information that goes out to the different parts of our bodies. We have sensors in our joints, in our tendons, and in our muscles that tell us information about the tension, the stretch, or the position of the body. So, for example, if we were to use something like a cockroach, we could have a cockroach leg in a position like this, and just like I did where I did extension and flexion, we could change the position of the cockroach leg and we would hear the electrical activity change. Only in that case, we wouldn't actually be listening to the muscles, we would be listening to the neurons firing. So it's a little bit different case there than what we have today. So that's a really good question about this idea of what happens if we can't lift something. I see some more chat questions and comments. Uh, yeah, so hopefully that answered your question about that. So if you can't recruit enough muscle fibers, or if you've maximized all your recruitment, we get to this idea of muscle failure. You can't lift it. You can't move it. It's interesting because psychologically, we can prepare ourselves for success or failure in terms of moving things with our body. So I don't know if this has ever happened to any of you. You might go over to a small box. This was a very reasonably sized box with not much weight in it today. But have you ever gone to a small box and it had something really heavy in it, and you had to give a little extra to lift it? That was the recruitment that we're talking about. If you've ever gone over to a big box and it was empty and you didn't know it was empty, or maybe it just had some packing peanuts, so if they still use those, or maybe it just had a pillow in it, and you thought, boy, I'm going to have to really lift this, and you just about throw it to the ceiling because your body was anticipating that motor unit recruitment that was going to be needed to lift that object. So yeah, those are good questions. So what would it look like if we were using different weights? What would it look like if we were at different body positions? What if I had my arm behind the rest of my body and then squeeze? So if I squeeze like this, would that look different? Would I be able to generate the same kind of electrical activity? Remember, we're talking about electrical activity, and we're not measuring the force generated or the tension generated. But we could, see if there's a correlation. Does this spiking activity, each of those little things that stick up like that, that's what we call a spike or an action potential. Now, these are compound because they're being measured outside of the body, outside of the cells rather than inside of the cells. But those are all really good questions, right? What would it look like if you say we're throwing a ball? And could you see the change across your deltoid muscle? So we have 3 different components to the deltoid. Are all of those active at the same time? You could use other muscles of the body. So with these thinner or smaller electrodes, you could get down here, and there's actually a really good video that we can watch on this from Backyard Brains that talks about these activities that you can do, right? So I wanted to get in here and start out with what we're doing today rather than just show you the video to start. Let's see here. Sorry, I've got to get back to the correct video. If you have any questions, please let me know. If I've gone too fast, let me know.
And for the folks longer term who are thinking about different ways to use this, you could also be thinking of your longer term questions. So we could revisit this and spend a little more time on the schematic part of it and some of the principles and all. If this is an important part of your experience, we can spend a little more time here and develop this a little more if you want to get a more fuller understanding of it.
Yeah, I haven't touched on any of the mathematics or anything like that. So if you want to get into even some of that a little bit, we can. I'm not a physicist, so I'm going to keep it at the biology level. But yeah, it's pretty interesting stuff. Let me see here. We want to share screen and share computer sound. So here's kind of the jazzed up introductory video from Backyard Brains. I've lost my play button somewhere.
backyard brains brings.
Sorry about that. Didn't mean to keep going. So yeah, there are just some ideas here about what you can do. We do have this extension activity, which uses the reflex hammer. Now this reflex hammer is something that you might see in a doctor's office, except this one has some electrical components to it. And there is an extra input area on our Spiker Box Pro. So it has this kind of an L-shaped connector. This L-shaped connector goes onto this part. So well, you can see that. So it goes there. And what this acts as is what we call an event marker. So if I tap this, it's going to basically register that tap and cause an electrical signal to be sent down the device, and that's going to be recorded. So let's see if we can record one of these being sent down to the device. Let me get back to the recording software. So I always have to select that I'm going back to the USB input. Again, the wavy lines are some of the what we call 60 cycle noise. Now, ordinarily, when we think about reflexes and reflex hammers, we think about the patellar reflex, and there is the patellar reflex. Just for the sake of trying to see what this looks like today, if we come down kind of the center of our arm, there's a tendon right there called the biceps tendon. So just to make sure I'm aiming for the right spot, I feel that tendon, a little mark there. So I'm going to try to hit that spot. So I'm not going to try to hurt myself, obviously, but I'm going to try to hit that tendon. Did you see on the bottom what happened? So on the bottom, we're getting this extra input. Now we're not seeing a whole lot happen at the top because I'm not getting a big enough reflex to happen. So my reflex is being very, very small, and plus I'm doing it to myself. So ideally, what we would see is something like this. I'm going to fake it for today. So what that would allow us to do then is we would be allowed to figure out the time between the hit and then the reflex contraction. So that's the last thing I really want to get into is this idea of reflexes. So reflexes are fast, automatic, and predictable responses to a stimulus or something that happens. So when we usually talk about these kinds of muscle reflexes, if you stretch the muscle, it will reflexively contract, and that's a protective feature. It also allows us to do these movements that are gentle and coordinated based on the fact that we have different tensions at different times in the movement. So if we were going back to the classic example of the knee jerk reflex, right? We have our knee, we tap, and the foot raises. It's hard to do a reflex test on yourself, and it's hard to do it if you're not completely relaxed, which I'm not. So here's a question then. So how does a reflex work? In the middle of our muscles, So I'll just go back to my biceps muscle again. So in the middle of my biceps muscle, there are these little special sensors in there called muscle spindle fibers. Don't worry about them being called muscle spindle fibers. There's not a test next week. Do know that there are sensors there. Those sensors detect the tension on the muscle. So if the muscle stretches, then it causes these sensors to activate. So if I hit that biceps brachii tendon just right, it would cause those to stretch. That signal goes up to the spinal cord. There's some communication and decision making that goes on in the spinal cord, and then a signal comes right back out to the biceps brachii muscle to cause it to contract in just a little reflexive twitch. Same thing with our leg, and we have our quadriceps muscle. If we hit that patellar ligament or that patellar tendon, it's going to cause a stretch, and that's going to be sent up to the spinal cord, and then the spinal cord is going to send the signal right back out to tell the quadriceps muscle to contract, and that's going to cause our foot to move in what we call the knee-jerk reflex. So here's something just to think about with this idea. So if we use this reflex hammer, it tells us when that signal was sent, and then if we are using the recording electrodes, it tells us when we saw the signal generated on the muscle. So there's a time from when the signal was sent until the time when the muscle activated. So that's the time lapse or the time lag between those two events. So we could try to figure out, is that always the same for different people or for different muscles? Is it always the same amount? We could even do something mathematically that's pretty interesting and try to give an estimate for how fast that signal traveled. So we could try to figure that out in something like meters per second, or even if we wanted to, miles per hour. So how fast does that electrical signal in that reflex pathway travel to get back to generate a muscle contraction in response? And what you would find is these things are happening very, very, very fast. Lickety split is a good everyday person's view of how fast they happen. They happen lickety split.
There's a question in the private chat about alcohol's influence on spindle fibers and this reaction time sequence you're talking about.
Okay. I don't know if alcohol has an effect on those muscle spindle fibers. Alcohol does have an effect on neurons in general. And since we have this big organ in the top of our bodies called the brain that has billions upon billions of neurons, those get affected. Alcohol does some interesting things, and by interesting, I mean not good things to the way our cell membranes operate. So they don't perform the same. So it's kind of like having a piece of paper that's separating these charges again, but now we have something that's kind of poking holes in the membrane and allowing some leak. So it slows down the rate at which we can send these electrical signals, at least in the brain. Whether that also affects the muscle spindle fibers, I don't know. But it would be primarily worrisome for the neurons involved, because the neurons are going to be carrying the long distance signal. So, for example, let's think about if you can wiggle your toes, right? So I'm wiggling my toes in my shoe right now. The neurons that control my toe wiggling, they start out up here in my lower back. So they're up here in my lower back. I'm not super tall. I'm just under 6 feet tall. So if we measured from this point in my back all the way down to my foot, we would find that that is over 1 meter long. So that one neuron, or those neurons that control those muscle fibers in the motor units of those toe wiggling muscles down in my foot, those neurons are over 1 meter long. So those individual cells are over 1 meter long. That's kind of crazy, right? They're over 1 meter long, yet they can send that signal like that. So I don't know about the alcohol effects on the muscle spindles, but alcohol does delay reaction times. So it disrupts the processing of these electrical signals in the brain. And so it wouldn't surprise me if it actually affected the muscle spindle fibers themselves, but those are going to be probably less important for that overall pathway of a reflex than the neurons, because they're carrying the long distance information. That's a good question, though.
Yeah, any more questions, please put them in the chat, or you can send them privately if you're a little bit nervous, or you can just blurt it out. My favorite.
Y'all have come up with some really good questions, though. I will say that. And see, I don't know if y'all noticed this, but I just said I didn't know the answer. That's okay, too. Somebody else might know the answer. A lot of times in my classes, I will say, what would be a reasonable explanation? Because I might not know the answer, but we can come up with reasonable ideas. And then, of course, in the science, what do we do with those reasonable ideas? We evaluate whether those are actually correct or incorrect, or maybe they're partially correct and need to be improved upon. And that's the whole scientific inquiry process. So in science, you actually learn more from being wrong than from being right. So questions are good. Let me see a show of raised hands. Has anybody been able to get this connected and try it, at least without the smartphone, just by playing it through the speaker? Have you listened to your own muscle activity yet? Anybody? All right, Ray. Thomas, all right. I don't know if you saw, did you pay attention to the guy in the video? His face, he started getting that Incredible Hulk face when he was doing his muscle contractions. I wonder what would happen if we put electrodes up here. Do you think we could put electrodes up here and put a recording, a reference electrode, and then record from these muscles? I wonder what those would look like compared to our biceps brachial muscle. Do you think they would be the same size, or would they be smaller? Those are all good questions that can be asked.
Yeah, something cool like comparing the muscle pattern with a fastball versus a curveball or something. If there's different movements, or I don't know, different ball throws or something. Something you could compare across people or across ages, or something that's pretty standard still.
Yeah, that would probably require looking at some different muscles. I would think that for baseball or softball pitchers, a lot of that type of pitching is going to be dealing with the muscles that control the fingers, which are going to be in the forearm primarily. So the ones that are going to do extension are on the back of the forearm, and the ones that are going to do flexion, right? Decrease the angle again. See that? Flexion, extension, flexion, extension. By the way, this is called hyperextension. So moving from flexion, extension, then you hyperextend. I can't hyperextend my fingers very naturally myself, but some people can. Some people have very flexible joints. But you could take measurements on your extensors and on the flexors, and you wouldn't necessarily even have to be throwing the ball. You could just be gripping the ball, and you could see what is there muscle activity, which muscles are being activated. And you could even try to locate individual muscles. So there's a whole group of extensors and a whole group of flexors. And you could try to figure out which of those are involved. And instead of actually having to throw the whole ball, Jeremy, you might just take it and bend at the wrist or something like that. That way you don't have to. One of the physical limitations, right, is if I am throwing a ball, I have to have all my electrodes hooked up and I have this cabling hooked up. And if I'm taking a big throw, if I'm throwing a softball, if I'm throwing a baseball, I could have issues. So I would start out with smaller motions to begin. Let's see, it looks like. So are there more muscles in a human's face? There are lots of individual muscles in a human's face compared to, say, our upper arm. So one of my genetic gifts is I have pretty good control over my muscle movements in my face. So I can do this. Not everyone can control their frontalis muscle on each side individually. So some people can only do this. So that's a genetic gift right there. I couldn't be 6'5" and play in the NBA or Major League Baseball, but I can move my eyebrows independently. I see Mr. Neville asked, why do muscles used on the farm work better for a 60-year-old than a 30-year-old? I don't know if that is something we would talk about in terms of conditioning, or if that's something we might talk about in terms of technique. Because, for example, since we've talked about sports and this idea of pitching, I don't know if people have looked at some of the statistics, but the average fastball has increased several miles per hour over the last 10 or 15 years. And it's not because the pitchers are bigger than they used to be or stronger than they used to be, but it's about the technique that they use. So there's a lot to be said about using the correct technique. So getting back to that idea, and this idea that Ray had earlier about the work, and if your task was doing something that you physically cannot do, you could see how somebody that's interested in what we might call human engineering or ergonomics might try to use some of these electromyogram recordings to see how much effort or how much activity occurs doing a particular task and try to design a more efficient or a better way to do it that could lead to less possible strain or damage. Yeah, Mr. Neville, I don't know what the major thing is there. I wish I had. I'm far off the chart for either of those folks. If I mow the grass, I'm hurting for a couple of days these days. Any other questions?
Yeah, so we're winding down. If anybody has any last questions about the muscle talk or some weird ideas for what could be measured, or anything else, or any other questions, I think you're just about completed. Yeah.
Yes, sir. Now, I will just say this. One thing else that I didn't get into is if you're on the app with the spike recorder and you're going to get all of those, right? There's a scale bar at the bottom that is matched to the time. So you can adjust that scale bar. Say you wanted to look at 1 second on the bar or make the bar to be equal to 1 second, or you could change it to make the bar be, 10 milliseconds if you want. Using that kind of thing and recording, we could actually count the number of spikes per second. So like we saw earlier, we had that little wavy line in there. That was the electrical line, or the what we call the noise. So we could actually set a cutoff point and we say, okay, if you're above this amount, then we'll count you as being an actual spike. And we can actually count what is the spikes per second. So if I squeeze really hard and held that as long as I could, we could see if the spikes per second change over time. Is it constant? We saw that on some of those we would get kind of a whole bunch at the start and then it would tail off, whole bunch at the start and then tail off. So how does that look in terms of, this is getting again to that more mathematical side. What's the firing rate or the spike rate for these muscle contractions? Is it always the same? So what you'll notice is as long as you're holding that tension, you're continuing to send those action potentials or those spikes across that muscle. How does it change? If you wanted to see how long you could hold 10 pounds up, right? Or maybe you want to see how long you could hold 30 pounds up. Does that change before you say, I get tired? And then that could maybe give you an idea of whether it's the muscle getting tired or whether your brain's just saying, I'm uncomfortable with this feeling. I don't like it anymore. So those are just some ideas to think about, things that you can try to answer. And certainly if you think of something later, you can always let us know and we'll try to work with you.
I'll just share that I really like what you had mentioned earlier about picking up a small item and it's heavier than you expected, and you feel your body kind of take a second stab at grabbing it. And then I was thinking about, athletes like MMA fighters, for example, they go way further than a regular person can. So they've in some way kind of artificially pushed out that memory, so the body's not responding to it in some way, you know. I don't know. It's really weird, the interplay, I guess, between the psychology and how it must be related to this electrical stuff. So where's kind of the line between those two things is really interesting.
And if people want to see how that works at home, it's a very simple thing you can do on your own. It's hard for me to do because I'm by myself. So uh, I will already know. But you basically just hold your arm out like this, and you don't have to be hooked up to any machinery for this, and have somebody put a book on it. Uh, you know, find a good human anatomy book or general chemistry book or something like that, or a dictionary. Dictionary is great. So you have your arm out like this, and somebody else puts the dictionary on, and what you're going to see is your arm is going to go down, but then it's going to come right back up. So that's that recruitment of the additional muscle fibers and motor units to get that accomplished. So again, if I had a small amount of lead, which is very dense, right, very, very heavy, I could put that in somebody's hand. They'd have to do that too, even though it looked like it was going to be light. Or you could put, again, if you had this and had the ends covered, somebody might think it had a few pounds in it. And then you put it on their hand and their hand might go up because they were expecting it to be heavy and it already went up. But that's just something you can do, and you don't even have to be hooked up to any of this apparatus for it. And if I may, Jeremy, just one last thing is I do teach biology here at Kentucky State University. We do offer degrees in biology. So we have a pre-professional track, ideally designed for those that are interested in going to veterinary school or medical school or dental school. We also have a general biology track that can be used for some of those purposes, or it can be used to go to graduate school, or for those that are looking to go directly into the workforce. And we also have a biology education track where students that want to become high school teachers can learn how to teach while they're learning how to do biology and how to do science. So we offer all of those, and I would be remiss if I didn't mention that this afternoon. So if you have any questions about those, I'd be happy to answer them. And it doesn't have to be now, but as you think about it, let me know, and I will certainly try to give you some information. I want to thank everybody that's participated today. I know we're all zoomed out, but I'm glad to see that some folks have already, we call it playing, but I'm going to call it learning with this equipment and thinking about how this affects them, or coming up with good questions. Keep coming up with them. You can't go wrong.
Bruce, I'm going to say thank you, sir, and give you a virtual round of applause here.
Well, thank
And
you.
if the participants, if y'all could do the same. Um, this does bring us to the end of the session. So we're done today. That was really cool. If anybody who wants to revisit that, because in the regular schedule, this content that we've been discussing, it won't make an appearance unless you go to seek it out. So if this is something you want to settle on a little bit longer, contact me, and we can get a conversation going and figure out what we can do productive with this thing over the next couple of weeks, if you're so inclined to it. If you don't have any interest in that thing, I would definitely come back and pick it up. We would definitely hang on to those. So that's it. If nobody has any questions, and I'll just pause for 10 seconds afterwards, and if not, then I'll just say goodbye, and I will be sending you another schedule that'll cover tomorrow. So tomorrow's all about computer science, and you'll have a schedule that'll detail the areas that we're exploring. I've been here texting with those guys about what tomorrow's going to look like, and I just really hope everybody shows back up. So are there any closing comments or questions? All right. Well, thank you all very much. The presenters, thank you for being on this morning, and thank you for hanging out the whole time. And Bruce, that was most excellent, sir.
Thank you.
All right. Y'all have a good one. I'll see you at 10 a.m. tomorrow. Thank you.